Hi, everyone. Welcome to the last Colloquium session of the season, and it's the hottest session, literally by temperature. So it's my pleasure to welcome József Varga. So he was a colleague. I know him since my years in Konkoly Observatory. So it was my first postdoc and his first postdoc as well. And yeah, I know him for quite some time. So yeah, he's a leading expert in infrared interferometry and key contributor in VLTI MATISSE project. So he got his PhD in 2015 from ÖAW University in Budapest, which is close to the Konkoly Observatory. And he has been involved in development and commissioning of this MATISSE instrument interferometer for about a decade now. So his research interests now are protoplanetary disk, young stellar object, inner disk structure, things like that. And his hobbies include hiking, rock climbing, running, and everything interesting. So yeah, József, take it away.
Thank you for the nice introduction, and I also thank for the invitation to be here. It's a very nice institute, and it's the first time I'm here. So I will talk about the inner region of planet-forming disks from VLTI observations. I will also try to show both some of the technical side of this observation, but more focus will be on the science. And let's start. Should I ask whether my voice is?
It's okay.
It's okay. Yeah. Anyway. So a little bit of introduction about star and planet formation to have everybody on the same page. So I'm interested in the material in this early phase of star formation, where we see a disk structure around the young star. This lasts about a few million years, and in this disk, which is rich in gas and dust, planets are forming. And after a few million years, this disk dispersed, and planets are evolving, but their mass is basically is acquired from the disk, and so the planetary system evolves in a different way from now on. For me, the most interesting in this phase where we see the disk more or less without the planets, and we try to guess, try to study what will be from this material which we see, what kind of planets will form. And also the other side, if we see some substructures in this disk, then can we do those structures tell us about the planets forming there. So how to observe these disks? First, I would like to show this slide. So this is how this looks like, different wavelengths. So how these disks emit light. Basically, it's just in the infrared wavelengths, it's blackbody emission. And in this phase, the central star illuminates the disk, and the stellar light gets absorbed by the dust, and then it will be emitted at several wavelengths, depending on the temperature. And usually, the temperature structure is so that in the inner part, we have like a temperature of a few thousandths of Kelvin at around 0.1 AU. And by the time we reach tenths or hundredths of AU distance from the star, this temperature drops to a few tenths of Kelvin. And that will set, it will set some important constraints of the observability in this disk. What you see here, there is a black area here near the star. It's because at that region, so close to the star, dust cannot reside because the temperatures are so high that the dust grains sublimate there. So there is just gas in this part, and the gas doesn't emit a continuum radiation usually at these temperatures. So it's at infrared modifier. And there is a radius where this transition happens. Usually this radius corresponds to a temperature of 1500 Kelvin. And this is the dust sublimation radius and the dust sublimation temperature. So if we have at this radius, we can have dust grains, and these dust grains will be quite hot and will emit mostly in the near infrared. So this ACD curve will in this plot. This blue is the emission component from that area. If we go to larger radii, then the disk material there will be colder, and that it will emit at mostly at longer wavelengths. And one thing that here a scattered stellar light is not considered in this picture. It can be important in the near infrared. And the other thing, also this, you can see some vague dark rings here, and that's because we expect that some substructures can be there with the disk, because in the last decade we get new observation, new high-resolution observations of these disks, which revealed the rich substructures in the disks at tens of AU scales. For example, this image of Tauri from ALMA was one of these first images, which showed this nice rich ring and gap substructure. And many disk observations then after that revealed similar ring gap substructures. Also at some cases, this is another type of observation because ALMA observations in the millimeter, which is more sensitive to the thermal emission from large dust grains, large millimeter size large grains, which are cold. And from this observation is from the SPHERE instrument and in near infrared wavelengths, where the scattered stellar light emission, that is what we see here, and we see here a nice spiral structure. So these are just two examples. But one might ask the question, what about the inner disk? And what do we expect ring or spiral structures in the inner disk as well? And the only method currently which can probe this is infrared interferometry. So what is interferometry? Small introduction. So we obtained information on an object by the interference of light. Okay, but why it is good for us? Because we can reach, with this technique, we can reach a higher resolution, which is needed to resolve the inner disk, because just to remind you, the inner disk in both of the image, the inner disk that I'm interested in is comparable to the size of this laser pointer dot here, in both cases. And that is where probably multiple planets are forming, multiple terrestrial kind of planets. And so what we do here is to have some telescopes and put these telescopes in an array, and so construct pairs of telescopes, and then combine the light of these telescopes in an instrument which will create this fringe pattern. And this pattern will carry information of the object, on the structure of the object. And the resolution will depend on the distance of the telescope. If it's longer distance, then the higher resolution which we will get. And if we have different combinations, different baselines, which will be probe the shorter spacings than the longer spacings at different position angles. Then we can, from these observations, we can derive the original, the structure of the object. It is, if we have many telescopes, then it's relatively straightforward, like this image again, but this ALMA image. ALMA is also an interferometer, and it is possible with those data to get this direct reconstructed image. If we have just 4 telescopes, as in the case for the VLTI, it is not as straightforward, but still possible. So what we measure here is in interferometry is a so-called correlated flux or visibility, which is the Fourier transform of the image. And we sample at some baselines. So this is this diagram shows what points we sample in the UV space. So one point corresponds to a telescope pair, and the distance from the center is the baseline, so the distance between the telescope projected, and the position angle is also the position angle of the telescope with respect to the sky. And what we want to achieve is that to populate this plot with as many dots as we have, but it's usually limited by our time, by the time that that we are allowed. So usually we don't have that much of UV points with our infrared interferometers. And what is on the detector is what is measured is this fringe pattern, and from the amplitude and the phase that we get this spatial data. So the amplitude is the visibility amplitude of this. And we have, if we have objects like one object or the same object but a different wavelength, for example, consider a disk which have a at some wavelength we just see the inner central part, and at another wavelength we see the ring structure. Then the visibility signal versus if we plot these measured values as a function of the baseline length will tell us about the separation and extent of these structures. And with some modeling, we can measure these parameters, so they measure the spatial structure of this object. Okay, so currently there are 2 main facilities for infrared interferometry in the world. One is the Very Large Telescope Interferometer in Chile, and other is the CHARA in the USA. And so both of our top of the tier observatories. For that, VLTI has 4 big telescopes and 4 smaller telescopes. Both can be used for interferometry, but at the same time, only 4 telescopes can be combined. CHARA has 6 telescopes, so it has better UV sampling, better wavelength sampling. So these are some technical details I want to highlight that, but I'm mainly working with VLTI data, and VLTI has 3 instruments: Pioneer in the near infrared, 1.6 micron, Gravity also in the near infrared, 2.2 micron, and MATISSE in the mid infrared. So MATISSE is the instrument which covers the broadest wavelength range in the VLTI, because it has L and M bands between 3 and 5 micron, and the N band between 8 and 13 micron. And that's good for this observation. It is very highly valuable if we get a broad wavelength coverage for our objects. And so we measure spectra. So at every baseline, we measure not every wavelength, and baseline we measure the visibility point, and then so these can be drawn as a spectra. So And as you see, this is an example for an N-band observation, where we have for the 4 telescopes, we have 6 combinations, so that 6 telescope pairs, and then we will have 6 baselines. And each of the 6 baselines, we get one spectrally resolved visibility. And that's what you see here. And this has a nice shape. This object that is observed here is emitting the silicate emission feature. So it is a solid state spectral feature emitted by small dust grains. And I will go back to this object later. Okay. So that was the introduction. I hope I have enough time for the science. So
Again, might you automatically, or because here it did come back? Come back.
okay.
Sorry for that. Yeah, it's good.
So I will continue now. Yeah. Can people online hear me?
They are there.
Okay.
No, they don't say anything, but
So first topic is this structures and time variability. And oops.
these are the online people. They say it's fine.
Okay. So I will show the example for HE163296. It's a very prominent and highly studied platforming disk. This is the ALMA image, and you see here these prominent rings and the gaps between, also some asymmetric features. Now, but it's not the inner disk. So let's zoom into another ALMA image. You can see the central 5 AU, 510 AU, where there is some asymmetry, but now ALMA has reached its highest resolution, and then that's the highest that we can get from ALMA currently, and it's not enough to resolve even more the structure. So that's why when we need observations, and you can see in the central part one such VLTI observation. So this was from the pioneer instrument, it's near infrared. And what you can see here, this is a model image. You can see here a ring. It's not very well seen because this ring in this model is quite fuzzy, it's smoothed out. But there is a strong asymmetry in this ring, which is modeled very well with this banana shape or croissant, if you are French. And this is at a specific location. So what if we observe this object again with this instrument or with another instrument, and let's check whether this stayed at the same place or not. And we observe this with MATISSE, and we get from the same modeling, we get this image. And what we see is the peak position for the asymmetry is different. So based on that, we said that there is an asymmetric structure at around linear 0.3 AU, and it's moving. And it's probably a dust cloud which orbits the star. That's good. We have this two epochs from this. based on the location and what we know about the mass of the central star. If it's Keplerian, it would be orbit in a period of between 20 or 42 days. It depends on where is the exact, where you put the maximum. Because you see in the Pioneer image, the ring is smaller than in the Matisse image. And this is because of some of the modeling. Because with this modeling, if we have just one ring, but the disk is in this region is like continuous from which starts right in a edge and then continues forward, continues outwards. Then at every, if we practically, if we look at at 1.6 micron and the Pioneer wavelength, we basically see the inner, this dust sublimation edge. But when we go to longer wavelengths, this is 3 micron, this Matisse wavelength, that we also start to see some stuff which is located further outwards. So that's why this ring is larger here in the Matisse image. So, okay, but what's because it was a few years ago. The new thing, oh wait, before the new thing, that might also be interesting for you, is that hydro simulation of this thing. And so we saw the formation of a unique large-scale vortex at the edge of the dusty disk because of Rossby wave instability. And the shape of this, so this is the simulation, and this is surface density, so we don't process radiative transfer, but the general shape is more or less similar to what we see in the Matisse images, at least the azimuthal extent of this block. So at least we can say that that the vortex scenario is compatible with our data. Then what about the new data? So, and here I will show Chara data. So this is a paper by Benjamin Setterholm and colleagues who used Chara data. So it's an independent group. So this is the Chara group. But I want to show this because they could observe with Chara on a higher resolution and better UV coverage, this object, same object. And what they did is to observe this at different nights. So they have a time series of observations, and from every night, they could make an image of the object. And what it showed that when they have a very good data with a good UV coverage, then they can indeed resolve this ring. And this ring has some brightness maximum. So an asymmetry it's a bit messier than this picture, because this picture is really a simplified. The reality is messier, but it's still consistent with the scenario that we will have a prominent blob, bright blob which orbits the star. So based on that, they measured the position and the rotation period of the blob, and that is what they get is 0.13 AU for the radius. It's quite small, and the surprising thing that the orbital period is 44 days. So 44 days, 3 times the local Keplerian period. It's reduced. And so, what is that? So they argued there were several scenarios. One scenario was that if we put the planet at 0.3 AU, that would have the Keplerian period of 44 days. And then maybe the planet induces some dynamical structures which will move at the same period. And maybe that we see here.
So there would be a planet outside of this.
Outside, so the planet would
can't
be
see
somewhere here, and we can't see in this data. What is interesting that from the Matisse modeling, we have this ring at 0.3 AU, And I put here, we have a similar date. So it is June 5. The MATISSE data was May 6 at the same year. And so I put here the expected location of the blob for the MATISSE epoch. And it is opposite of the position that we measured with MATISSE. So it definitely needs some follow-up studies. And we have MATISSE data that we will do also similar time series analysis. Okay. I will show another example for the time variability aspect, and it is the case of the BX-CHA system, which is a spectroscopy binary. And this is the work of my PhD student. And what we have here is 2 stars and some dust around it. And we have MATISSE data, and she modeled the stars are they move on Keplerian orbits, and this Keplerian orbit is constrained by radial velocity measurements. And also the model included a ring, an asymmetric ring of dust. And these are the best fitting model images for 3 of our epochs. Epochs. And you see that this arc, this dust arc, is not staying at the same location. So here we again have the situation where there is most likely there is a moving dust structure. But what is the dust structure? It is yet unclear, because in normal case we wouldn't see a ring, a dust ring at those locations. Numerical hydrosimulation shows that for such binaries, this is an eccentric binary. So if you have an eccentric binary, then the binary will carve a very big cavity in the disk. And if you compare the size of the dust we see in our data to this simulation, that you see that it is not compatible. So what is that? So based on this, we argue that what we see in the MATISSE image is not a real disk. It probably comes from these accretion structures, accretion funnels, which are, if they are close to the star, they can get quite hot, so like several hundreds of Kelvin, and they will emit at this wavelength, at the 3 micron. But we don't see this outer ring, outer disk at this wavelength, because probably it's too cold and too dim. So I think that's also a very nice result. So in the next part of my talk, I would like to talk about this dust. And first part of it is still substructures. So this is the disk of HG14442, where we collected a complete data set from the VLTI. So it had all the 3 instruments. So the wavelength coverage is from 1.7 micron to 30 microns. It's very nice. And with the detailed modeling, we could reveal nice, interesting ringed substructures. And this was only possible because the good interferometric baseline sampling and also the good wavelength sampling. So this is a simple physical model. It's a temperature gradient model, and so it's every ring of these are elliptical. This model is made of thin elliptical rings, and each ring has its temperature. The temperature is a simple prescription. It's a power law. So it starts at 1500 Kelvin at the inner edge of the dusty disk, and then it has some decrease. Okay. And what we see here in the near infrared, that we see the region which is very close to the star, they're very close to the dust sublimation radius. But what we see at longer wavelengths, in the thermal infrared, we need the other ring to explain the data, so that we see the contribution from a second distinct ring, and even more in the end band, we have a third ring. So this is constrained by the data. So because this modeling was started with just one single continuous disk structure, and that did not fit the data. Then I tried two-ring model, and that did not fit either. Then the three-ring model was the simplest model which fits the data well. So three rings. What about that? And the other part of this study is not just because this kind of modeling is not just revealing the structure, but also revealing the dust composition, because we have also the end band, where in the end band we have this interesting shaped silicate spectral feature. And if we want to account for the shape of this emission, that we have to include the opacities, the emission of the various dust components in the disk. And what you see here, that what we have here is in these transforming disks, this dust is made of silicates, mostly magnesium silicates and some other stuff. But the most contribution to the light is coming from these small micron, submicron size silicate grains. And there are laboratory measurements for the optical properties of these silicate grains, and these laboratory measurements can be compared to the real data and can be used as a template to fit these spectra. And what we have here is usually that we have in this spectrum, we have a mix of different kinds of silicates, different chemical composition, different crystallinity state, and different grain sizes. All of them mixed together. And here, what I show here is the optical opacity profile for several minerals. And what you see here, I think what should be remembered here is that we have we have the crystalline silicates, which have ordered structure, and these show distinct and small peaks. But we can have the same kind of material, but with a disordered structure. So that's analogous to the glass. And in that case, these small subpeaks disappear, and the whole shape is more like a broad triangular shape. And with this, if we include these things, then we can account for the spectrum. But we also know that there should be not just silicates, there should be other materials in the dust. And we can ask what is that material? And that is important to produce the continuum, the continuum emission, because silicates at short wavelengths in the near infrared are very transparent. And we need some other material which will produce that near infrared emission. And what can it be? So in many models, it is assumed that it is carbon, so amorphous carbon or graphite grains. And that is one possibility. But other possibility we considered in this modeling is iron, solid iron grains. So we did two modelings. So one is the silicates plus iron, and the other is the silicates plus carbon. And both fits are relatively good, except here in this region, just short of 8 micron, but the iron-rich model gives the best fit. So based on that, we stated that we have evidence for iron-rich dust in this disk. And I think this is the main message here. So we have the 3-ring inner disk at these locations and the evidence for solid iron grains. Okay, but why is that important? Because if we have such a model, if you have such a situation that this can be very related to the solar system, because then if we break up this the minerals and then derive the elemental abundances for the dust in this disk, then what we see, it's very similar to Mercury or Earth, just the iron is a bit more than in Earth and less than in Mercury. So it's an in-between case. But it can be very, very related. If we assume that all of these dust is not iron but carbon, then it's not possible to relate it to any kind of solar system or object. And it's important because I think we can think that it is some kind of universal that we have, okay, with some dispersion, but that we have carbon poor composition for these dusty disks. Another angle that we explored. What is this?
Right.
Is my time is up? Because
No. Just.
System.
I hope not. I have still several slides. So another angle that we approach this issue is chemical modeling of the dust condensates, and this is Peter Wojtke with his GG-Chem code. We produced abundance profiles for this condition for this disk. So basically, that is here that there is a temperature dependence, and also the temperature can be related to the radius, the specific radius from the star in the disk, and assuming some same assumptions on the pressure profile, then we get these abundances of different solid components in the disk, assuming thermochemical equilibrium. And for the solar abundance, what we have here is that the most abundant material in the inner part of the disk, inner 2AU, is iron. And the second one is this red, this is the forsterite, the Mg2SO4, and the third is blue, MgSO3, which is astatite, so both and magnesium silicates. And this is perfectly consistent with our picture that we get from these interferometric observations. One might ask why, so why then we don't see any carbon here? And it is because carbon, that in this, under these conditions, there is a lot more oxygen than carbon in the gas phase, and any remaining carbon will be locked up, will be locked up in CO, so it will make carbon compounds in the gas phase. Correct me if I'm wrong. So especially also some papers tell that there is a specific temperature around 900 Kelvin where this transition can occur from where carbon will combust in the disk. Okay, so this is solar abundance. What if we increase the C/O ratio? So what we see, if we put a very high C/O ratio of 0.95, that we start to see the solid carbon appearing. So here is this yellow line. And if we reach C/O to 1, then here it is this gray line. So this is the gray line, is the solid carbon. So there will be solid carbon. But the other thing is that there will be also silicon carbide in the disk. So under these conditions, with the C/O ratio is high, that every time silicon carbide good form. And why is it important? Because silicon carbide has infrared, mid-infrared spectral feature. Carbon doesn't have any features. So carbon is basically with most of these spectral analysis undetectable or very hard to detect, but silicon carbide is easy to detect. And I think it's an important thing that we do not regularly see silicon carbide. It's just very few and very special systems when we see silicon carbide. Also some AGB stars, for example. And so the message here that please, if you model this disk, consider iron as a main component in the dust within the inner regions. Oh. With that, I go to the third topic, is the ability to detect companions. So with these interferometers, we can also detect stellar and substellar companions to this, and also to stars. And I will show one result, which is done by me. This is the PCRA, it's a Herbig A star, and it has a complex circumstellar environment. As you see here, this is a sphere near-infrared image, and you see here this. So the thing in the middle is the coronagraphic mass, the shaded out region, which is blocked by the coronagraph of the instrument. So these two wings here is actually a ball-shaped surface of the disk, which is almost edge on, and the dark plane is this mid plane of this disk, which is almost edge on. So this is the surface of the disk, and from this study they said that okay, we also have this feature and this feature here, and so they said that this is also disk. It's an intermediate disk. So this is which is a bit smaller than this, and almost perpendicular to this, to the main disk. And why is that? Because they suspected from earlier spectral astrometric results that there should be a binary companion to the star somewhere along this direction. And what we see, what we have in VLTI with MATISSE, what we have is exactly this. So it's this is the image which we also model image that we constructed from MATISSE data, and we detected this companion. I will zoom it in. So you can see here is the very compact disk of the main component. It is because it's thermal emission from the warm material, and so all of this material in this black area is too cold to emit significantly at 3 micron. But so here we have this one, and also here we have this one, the companion, and this is 23 AU away from the main component, component with a few percent of flux ratio. So this was a nice surprise for us, and also it totally makes sense in spite of the former observations. Okay, then what if we go from a few percent of companion flux ratio to thousands? Then we reach the regime where exoplanets are. So a few years ago, the gravity instrument was the first interferometric instrument which could observe a planet and the planet spectrum. And now with MATISSE, we had some improvements, and now it's also possible with MATISSE. And so we have handful of exoplanets that we plan to observe. And the first is Beta-Fig B. Beta-Fig B is the brightest one. That's right. Is good. So it's a relatively large, massive planet. And I will show the 5 minutes. Okay. I will show quickly the spectrum. So here what we see is the spectrum from different instruments. This is under division. So here what we know that the more is purified and the green one is already interferometry. So this is the gravity and the new spectrum. And in between, here we have the MATISSE spectrum. And the size, because now this is almost complete. The 1 to 7 micron spectrum of Beta-Fig B is almost complete. This is very nice result, and that we could, based on this atmospheric modeling, we could do some constraints on the C/O ratio. So, and it's now there are other candidate planets that is some observations. Okay. So in these last 5 minutes, I would like to show something. So it is about modeling this data, interpreting this data. What you see here is a typical VLTI data set. It's from the MATISSE instrument, and what we see here is a visibility signal, a function of baseline. So what you see is what is this drop. So this drop of these points tells about the spatial extent. If it stays constant, then basically it's very small. So that means that it's a star. If it's then how this drops, what is the shape of this curve? The spatial structure. And the other part which we measure is the phase, the closure phase, so-called closure phase, and that tells us about the asymmetry of this field. But how do we go from the image, the reconstructed image? And actually what is done in the modeling is not this direction, but this direction. So from image to the simulated data. So what we have usually we assume some shape with some model parameters, and from the model parameter, set of model parameters, we compute a model image, do a Fourier transform, and we get these simulated observables. Then we do a data model comparison, and then we get some chi-square. Yeah, and then put this thing in a Peter algorithm, CMC, whatever. Then you can optimize the model parameters, and that's how it is done. So this is forward modeling. This is because there's just a few points, so we cannot do this direct just Fourier transform these points to get the image. And for this, we developed in the MATISSE team this software called OI Modeler. And this is the third generally available tool for modeling OI, optical interferometric data, and we think that it is the best. What is good in the that it is easily expandable. There is a good library of pre-built shapes, but it is very easy to define new shapes and new modules of this program. And it's already available on GitHub. And why is that? Why am that talking about? Not that. It's because I have with Peter Wojtke and Kundan Kadam, they invited me to start a little project with Life for Disks to explore the possibility to use this OI modeler for simulating life observations on disks. So Life, as I think many of you know, is the large interferometer for exoplanets. So it's a planned mission concept to put a an interferometer in space. And why would they do that? It's because in space you can get the needed sensitivity to detect terrestrial exoplanets. So that's the main objective. But apart from that, we are exploring the possibilities to use light for disks. And that's what we plan to do there, plan to use OI modeler to simulate and do some tests with this. So that's the end. And here is my summary. Thank you for your attention.
Thanks, József, for a really nice talk. Yeah, when you're interested, the time flies. Yeah. Okay, so yeah, questions. Yeah.
Okay. I have two questions. One of them very technical, maybe the first. When you showed the emission spectra from MATISSE and gravity, there's an offset in a flux, right?
In
Yeah,
this,
that's
a big one.
huh?
This one.
Yeah. Between gravity and GPI, or what is this?
Yeah, it's GPI and gravity. There is an offset in.
Yeah. You think it's real or is it more instrumental?
I don't know.
Yeah, because we have a similar thing with actually gravity and symphony, and we also don't know. So I was wondering if you know. Okay. The other question is more for the silicate features, right? We have this very nice spectra for the amorphous and crystalline silicate features, and it looks, yeah, this one. It looks like that zone 1 seems to be more crystalline.
Indeed. Yeah, that's what we get out of this data, because what is shown here is just a single dish flux.
Yeah.
And with in one slide I showed, yeah, I will show the slide where, yeah, here. This is the interferometric data, and the simple approach, if you think this spectra as an emission from localized area, and the size of that area is dependent on the baseline. So if you have larger baselines, then the emission you get is from that compact small area which is connected to the baseline. So that means, for example, at the longest baseline, we have these emissions come from within the inner 0.1, 0.5, 0.3. So what you see here is that these first two, so this is shorter baselines. So these shorter baselines contains both of this very inner disk and also something from this outer ring, so from this 1 AU or maybe 2 AU thing. This one is also the flux is smaller, then this can be regarded as the flux coming from the inner AU. And what you see here is the shape of this spectrum is totally different from this, because you see here a prominent 11.3 feature. So that's from crystalline phosphorite. And this constrains our model that within this 1 AU zone, we have a much more crystalline material.
Which makes sense, right? So
yeah.
the inner disk is warmer, it's also more maybe irradiated, it's more exposed to stellar high energy particles or whatever. So it's easier processed, and that's usually how you get crystalline. You have to break bonds in order to reform.
Yeah, indeed. So laboratory experiments show that at temperatures higher than 900 Kelvin, these materials undergo annealing. So this produces crystalline structures.
Yeah, that's funny, because in the hot Jupiters we don't see this. We have hotter temperatures and they still are amorphous.
That's very interesting.
Yeah, thanks.
But it's very regularly seen in protoplanetary.
Yeah, exactly. That's the fun thing, right? That we are seeing now similar things in different environments. And you say like, oh, temperature, and I tell you, no, it's not temperature. In some environments, apparently, even at this high temperatures, don't have crystals. And I wonder, and I also try to figure out why.
Maybe the pressure,
Huh?
maybe the pressure also.
Yeah, the pressure is obviously higher than this, right? Yeah, anyway, so that's why I was. So it tells you basically that these inner regions are hotter, and that's why you form the crystals. In the outer polar regions, you tend to have more this amorphous silicates. Okay, cool. Thanks.
Any other questions? Maybe the last question.
No, go ahead. I have a very naive question. This is not my field. The ALMA image you showed in the very beginning of the disk. Yeah. Why isn't it dark in the center of the disk? If like it's supposed to depict the dusk.
Yeah, because we don't have enough resolution.
Okay.
Just not resolved.
Okay, last two.
Really very tiny.
Last question, yeah.
Last, I have two topics, so quickly, or I don't know. Yeah, maybe on more interesting is on this bright spot that you're mentioning. You said it might have a period of 20 to 40 days. What limits the possibility of having observation every 10 days and see if it actually rotates? And second question is this not due to a tilt of the disk with respect to the observer and some sort of line of sight and radiative transfer through the disk?
No, it's not tilted because really it's changing its position. So you can see it's here, then it's a bit, okay, it's a bit tricky because unfortunately, there is no epoch where we see this thing on the other side. So definitely we need more observations. Maybe there is some effect, you said that about the inclination effect, that's also there, but and it's mixed with this real rotation. And that's why we don't see the blob at these positions.
An observation campaign on MATISSE every 5 days.
So with MATISSE, we have so this is not MATISSE. So this is Chara. But with MATISSE, we also have time series of that, and the cadence is very uneven. So we have like we have 1 day difference, we have 2 day difference. It's very very uneven. But our observation sequence now spans a few years, and I hope that we can get something out of that, something really useful. But it's really hard to do this. Yeah, again. Okay, so that's a closing. So on VLTI, we compete with many other programs, and it's not tuned for time series observations. It's just the best effort, and usually what we require is a good baseline coverage per night, and then do the same then the next day or maybe 2 days later. It's very very challenging.
Maybe we can thank our speaker and you can ask him questions later. There's a dinner at Francis Kana Keller restaurant, and we don't have many people. So if you want nice conversation with József, feel free to join us.
Okay. Thank you.